let's talk about the Doppler effect. So the Doppler effect is this. It's the apparent shift in frequency when wave source is moving relative to the observer. That says observer. Wow. Observer. Okay. So what does that mean? Well, this could either mean that we could view it as the source is moving and the observer is still. And that's kind of what we'll do the math with. But you could also have the source being still and observer is moving. Or they're both moving. Okay, and I guess that's what we mean by relative, right? A source and an observer are moving relative to each other. So let's do an example of what we mean by this. So let's say we have an ambulance. Here, I'll draw an ambulance. That does not look like an ambulance. No, we'll get it. This looks like an ambulance. There, we got that. This. Ambulances have these. And we have this. Okay, and an ambulance sitting still goes wee-oh, wee-oh, wee-oh. Okay, so we're all hopefully familiar with an ambulance, and it makes its ambulance-y noise. And what we'll do is we'll try to like understand what happens when it sits still versus what happens when it is moving. So let's take some circles. Let's imagine that these represent, that is not a circle. Let's imagine that these represent the waves moving out. What is going on here? The waves moving out from the ambulance here. Okay, there we go. Got a little bigger. A little smaller. It's going to drive people nuts here. Here, you know what? I'll pause while I get this thing sorted. Okay, so what we should have here is if this is the source of the sound, we'll put a little S right in the middle of it. And the ambulance is not moving currently. It's going to put sound out in 3 dimensions, right? We can only really show 2 on here. And you're going to have a consistent wavelength, right? It's going to have some frequency, okay? And all of these waves will be exactly equidistant from each other, okay? So in other words, our wavelength is constant in all directions. So what that means is if you are listening to this ambulance that's sitting still, it's not moving, you're standing over here somewhere in front of it. These waves are going to move towards you, and you're going to hear the frequency, let's say it's, I don't know, 440 hertz, exactly at 440 hertz. And if you're standing behind the ambulance, you're also going to hear the sound at 440 hertz. Okay, perfect. That's just normal listening to sound, okay? But if the ambulance is moving, something different will happen, okay? So we know that sound speed in air is set, okay? And we know to get that velocity in air, it's 331 meters per second plus 0.6 times the Celsius temperature. So, I mean, on like say a 20-degree day, you'd be at, say, something like 343 meters per second, roughly, okay? Well, what that means is regardless of how fast the ambulance is moving, when those sound waves get into the air, they will begin traveling at that exact speed that we have there, okay? They just stay at that speed no matter what. And this has an interesting effect. What it means is if the ambulance is moving in this direction, it is moved forward a little bit before it lets the next wave out of it, okay? And the same and the same and the same. So in other words, it's moving towards the waves that are moving away from it, and that will compress these wave fronts out in front of the ambulance. And out behind the ambulance, the waves will elongate. So what we'll do is we'll try to demonstrate this. I'm just going to pause for a second, fix up my picture. Okay, so now the ambulance is moving, and it's moving in this direction. Okay, so it now has some velocity forward. And let's say it's moving at like 25 meters per second. Okay, 25 meters per second. And we've got our frequency at 440 hertz. Okay, and so we'll call this like the velocity of the source. We'll call this the frequency, right? That's the frequency that the ambulance is putting out. Okay, the actual frequency. Let's call it Fs, frequency of the source. And then we need the velocity of sound in air. Let's call that V, let's say. And that is, I think we said 343 meters per second. So let's think about what's happening here, okay? In between each of these wave fronts, all right, the ambulance has moved 25 meters per second. Okay, so it's moved some distance forward based on the amount of time that there is between each of these emitted frequencies. So we could actually calculate this. We could figure out how much the wavelength is shortened by in front of the ambulance. Okay, so let's figure out how to do that. The first thing we got to do is we got to figure out the period of these waves. Okay, so the frequency, that means we get 440 waves per second. Well, how many seconds then is each wave? How many seconds between each emitted wave? Okay, so it's just the inverse of that. Actually, 2, 3. We'll be a little more careful. All right, so between each of these wave fronts, we have like this fraction of a second, right? Like 23 1,000ths of a second between each wave front that gets emitted by the source. Do you agree with that? Now, when this thing is sitting still, when this ambulance is sitting still, okay, your ears are going to hear each wave front hitting them at 0.0023 seconds. Okay, so now we can figure out what wavelength we would have. Okay, what wavelength we would have if we have this frequency and this period. Or sorry, this velocity and this frequency. So let's figure that out now. Okay, so my wavelength then. So if we know this is true, V equals F lambda, my wavelength should be equal to velocity divided by my frequency. So this is the velocity of the wave in air, right? So it's that 343 meters per second divided by the 440 hertz. So this is the true wavelength, right? This is the true wavelength of the wave when the ambulance is sitting still. So we've got about 0.78 meters for a wavelength. Okay. All right. So at 440 hertz, on a day when sound is traveling 343 meters per second, each wavelength for a still ambulance is 0.78 meters. Okay, but now realize this. Before the next wavelength can be emitted, this has moved forward a little bit, thereby shortening the wavelength. So we can actually figure out how far it's moved during the space between emitted wave fronts, which of course is 0.0023 seconds. So let's figure that out. How far forward does the ambulance move between wave fronts? So we're talking forward now. Well, say it just emitted a front, then 0.0023 seconds later it emits another front. How far did it move in there? So we take its velocity, which is 25 meters per second. So distance is equal to velocity times time, right? So how far did the ambulance move before the next wave front is emitted? So 25 meters per second, it's not very far, times 0.0023 seconds. All right, so that's how far the ambulance has moved before the next wave front is emitted. Okay, so that ambulance has moved forward 0.058 meters. It's moved a little bit, right? Like almost 6 centimeters. So what does this mean? Well, it means this. If we're looking at just in front of the ambulance, right? Here's our normal wavelength, right? Here's our normal wavelength. But before this is emitted, this ambulance has moved 0.058 meters forward. So our wavelength then is actually shortened out by that amount. Okay, so the new wavelength then in front of that ambulance is actually the difference between these two values. So my new wavelength in front equals 0.78 meters subtract 0.058 meters, because this is how far it's moved, right? This source has moved from here to here before the next wavelength can be emitted. If it was sitting still, we wouldn't have to worry about that. Each one is just that 0.78 meters, okay? So in front of the ambulance then, and we'll call this lambda, say, prime, because it's our new wavelength that we're going to have in front of the ambulance. It's not the actual emitted wavelength, but it's the wavelength that we're going to have apparently in front. We call it the apparent wavelength or the apparent frequency. Because the source is still emitting at whatever frequency it has. It's just that now we're moving along before those new wave fronts can get out. So this works out to about 0.722 meters. So a shorter wavelength. So then what frequency are we going to hear in front? So we'll call this the new frequency, or the Doppler shifted frequency, if V equals F lambda, then F should be V over lambda. And of course, it's lambda prime. This is still the velocity of sound in air. So 343 meters per second divided by 0.722 meters. This will tell us the new frequency of the ambulance. I get about 475 hertz. Right? We have a shorter wavelength, but the sound is still moving at the same velocity. So it's like a train with smaller boxcars going by at the same speed. You're going to have a raised velocity in front. Okay, so in front, you can see the waves are compressed. You have a higher frequency when you're traveling at 25 meters per second. You hear like something like 474 hertz in front of this ambulance. But then what happens behind? Well, now as each wave front is released, the ambulance has moved forward some value. So you're going to elongate out behind where these wavefronts are. So we're going to use the same exact logic. We're just going the other way now. We're not moving. We're not chasing the waves. We're running away from waves that are moving away from us in the opposite direction. So let's try that. So here's our normal two wave fronts. Okay. And remember now the waves are traveling in this direction. The waves are traveling this way. The waves are going backwards. And you're like running away from them. So you're doing like this. Okay? So here's the normal wavelength, but now you're moving away. So your new wavelength is actually this. We'll call this double prime to say your new wavelength behind is going to be longer than your actual wavelength. So this is still 0.78. Okay, but now you're elongating by this much. So D equals V times T. The distance that you're elongated by is your velocity, so 25 meters per second, times the time again for one wave, or the period, which is, I forget already what that was, 0.0023 seconds. So in other words, the source, right? The source of these wave fronts right here has moved a little bit, okay? And of course, it's moved the exact same distance it did before. It's just now that it's elongating rather than compressing, so 0.058. Or is it 0.0058 meters. So it's moved like 5 centimeters, almost 6 centimeters. All right, so now all we have to do is we just take our old wavelength, our 0.7, was it 0.78? Yeah, and we add now. We add to it. So we make the wavelength longer behind the object. Okay, so a longer wave. So what frequency is that going to be? So this is our new double prime wavelength. The velocity of sound in air, of course, has not changed. It's still 343 meters per second. And we just go back and we do the same math. Again, B equals F lambda. So then F double prime, this is the frequency behind the object. Sorry, you know what? I rushed a bit. It is actually only 1 0 in here. Let's just fix that up. Okay, so we'll just redo this value. Should only be the 1 0 there. I got excited. We'll fix it. So this should be 0.84 roughly. Okay, sorry about that. Anyway, the new frequency then is the velocity of sound in air divided by the double prime or the secondary wavelength. So we've got our 343 meters per second divided by 0.84 meters. And we get a frequency behind this ambulance of 408 hertz. So let's just think about that. The actual ambulance is doing this. In front of it, if it's traveling in this direction, we hear 475 hertz. And behind it, we hear 408 hertz. So this explains the obvious drop in pitch as an object moves by you with its horn blaring or if it's an ambulance. You get that meow, meow sound. So we can derive a formula to put all this information together, but to be honest, I think it's much more sensible for you to understand it like this than to just be thrown a formula and then you're in the hands of the formula and you're not really going to understand what you're doing. But I guess I can give it to you anyway. I'm not really even going to explain it. I'm not going to derive it, but it's derivable. Essentially, you're just combining what we did here into one like big equation. And there's other versions of this, but okay, that is what you're doing here. Okay, if you just start using this blindly, though, you're gonna screw up. So I don't recommend it. It's not necessary, but like if you're say into like doing some engineering or something, and you just want a formula to pull out and use, okay, there it is. But to me, forget about that. Use this method. It will make more sense to you, and it's worth it in the long run. Once you fully understand this, fine, start using the formula. But if I just give it to you, I know what'll happen. People will just go immediately to the formula, and they won't actually learn the concept.